Okay, so our speaker today is Julia, who is visiting us from ETH, and she's going to talk about her work on sizing solar and battery for EV-enabled homes. I don't know why we're getting this recorded. Okay, anyway, I think that message will disappear in a second.
I think you have to press.
Oh.
Patient.
Right, okay. Thank you.
Okay, thank you, Fisher, for the introduction, and welcome everyone to this presentation. I'm glad to see so many in the meeting today. After last week, I was expecting maybe 2 people, so it's great to have an audience. So today I'm going to talk about Solar Explorer, which is a tool to instantly give sizing recommendations for PV systems, including battery. So basically, it tells you how many panels you should get and what battery capacity. We do this because we found that the tools currently built to homeowners are very limited. So we wanted to build a tool which is very easy to use. It only requires simple inputs and it gives you accurate sizing estimates. By doing so, we hope to kind of show the costs and benefits of different configurations and ultimately hopefully motivate users to go forward and buy a PV system. So we'll start with some bad news, which is that despite a lot of advances in renewable energy, still about a third of the world's CO2 emissions are caused by the energy sector. So you can see here all of the emissions by different sectors, and you can see electricity and heat is by far the worst. Even if you remove the heat part and only look at electricity generation, it's still the highest emitting sector. There have been some countries driving a lot of progress, like China, who are building a lot of wind and solar farms. However, there's also other countries like the US who are kind of pulling away, so that's very unfortunate. However, there's also good news. So the cost of solar panels fell by approximately 93% since 2008. So this combined with different financing options, the declining battery prices, and depending where you are, also government incentives, has become really affordable for users to get the PV installations. And you'll also be paid back for your investment with reduced utility bills and the higher resilience to fluctuations in the energy prices. So we've seen during the pandemic how volatile those can be. So it's definitely good to have some self-sufficiency there.
You should point out this exponential curve. The y-axis is like this.
Yeah. So yeah. So I think it's much easier to motivate building owners to get PV systems if they also have financial benefits other than and not just for being green. So I think there's a lot of hope here that we'll see more deployment on the residential level. So if you're a homeowner and you decide you would like to get a PV system, one of the first things you're going to ask yourself is how much is this going to cost? And this mainly depends on how many panels you get and what battery you want, and if you want a battery. However, this question of sizing is not easy. It depends on a lot of factors. So we essentially do sizing estimates based on load curves and potential PV generation over a certain time. And those are very much misaligned. So ideally, you would have the peak production when there's also the peak production, but that's not the case. So for the production, we usually see a peak during around midday in summer, whereas the load is usually highest in the evening in winter. So this makes it very difficult. Then also we do those sizing estimates based on historical data. So we have to make sure that the sizings are also future-proof so that they are applicable in future scenarios where you might use a bit more loads or have a lower production. So you need to add some buffer there. And then finally, we've seen a lot more EVs on the road in recent years, partially because of reduced prices, but also some governments putting regulations out which ban the sale of new petroleum cars by a certain date, which is 2030 in the UK. So those EVs, they significantly affect the load curves. Overall, you have a higher electricity consumption. and the peak of that consumption might also shift. However, we shouldn't only look at EVs as a burden, but also as an opportunity, because as I already said, it's usually not a problem of producing enough renewable energy, but it's about when you produce it. With the EVs, we have a lot of new batteries standing around when they're home. So if you manage them carefully, you can charge when there is a lot of production, and even use the electricity to power your house at night if you use bidirectional charging. However, it also needs certain integration into the sizing estimates. There's been some prior research on this topic. For this project, we mainly look at simulators and ML-based methods. So simulators, the most recent ones, a lot of which have been developed by Keshav and previous students, they mainly get sizing estimates by trying out different PV and battery configurations, and then figuring out which ones meet a certain system target. So in this project, we will look at self-sufficiency. So if you want to have a 50% self-sufficiency, you want to have 50% of your loads covered by PV production. So we try out a lot of different configuration, and we get a robust sizing meeting that target. With robust, I mean that it will be with a certain confidence fit for the future, where you have some variations on the load and PV production. So those tools are very accurate, but there's one big problem, which is that they are slow. So with the most recent simulator developed by Anais and Keshav, takes around 1 to 2 minutes for one simulation, which is not so bad. But if you want to do like some larger scale evaluations, maybe show different configuration for different self-sufficiency levels, this quickly sums up, so you can easily compute for a couple of hours. Because of this, we want to replace simulations with ML-based methods. There has only been very limited research with ML-based methods for sizing. I mainly found two that I found were relevant. One of which only predicts the PV sizing, so how many panels, but it doesn't consider battery at all. And the other one predicts only based on your location and your self-sufficiency target, but it doesn't consider when the peak load is. So it's also quite inaccurate. Additionally, tools are not robust, and EVs are not considered. To address this, we developed SolExplore. So you can see a system overview here. Essentially, first, I will just run through it very quickly because I will explain in more detail later, and also show you a demo a bit later on. So first, the user gives some inputs. It was very important for us that we only require inputs which are easy for users to get or they already know, because a lot of the tools previously, they required load curves over a certain time, which are not accessible to users. So essentially, you can't really use the tool. We use that user input to generate the load curves, PV generation, and also EV usage traces. And we pass that to the model, which predicts the optimum battery capacity and the size of the PV system. Because we now use a model, it's much faster. It takes less than 1 millisecond to do one prediction. So we can basically predict as many sizings as we want. So now we can create certain curves. We do a cost curve where we have one prediction for every self-sufficiency level, and you can see how the cost increases. We also show yearly savings curve and a payback time curve. And then the users can explore a bit. Once they find a sizing which they like, they can then verify it with a simulation. This is important because while the model is quite accurate, we are dealing with multiple thousands worth of investment here, so models can have outliers, and we just want to make sure that we do not suggest sizings which are very off. I'll now.
So can I ask something?
Yeah.
Do you take into account the geometry of the building as well? Or?
Not at the moment, but that's actually future work, and I'm going to start working on that next week. Yes. So I will talk a bit about how we build the model now. We require 4 types of input. The first one being PV generation curves. So those are hourly traces over 1 year, when in each time step we have how much electricity is produced. And we have that for a lot of locations around the world. There's some gaps here in around Russia, Kazakhstan, and Argentina. This is due to just insufficient weather data, so we couldn't get traces, but it covers the majority of climatic regions. And we also do some adaptations because the cloud coverage over the years can vary, and also the overall production. So we scale the curves a little bit to just grow our data set, and we create gaps, kind of simulating that there will be more cloud coverage, and we also bridge gaps to just grow the data set. Then we require the household load traces. So those are the most difficult to get. There are only very few data sets, and usually they are quite small, so only about maybe 20 buildings, and usually also mainly in Europe or in the US. So because we need a quite large data set, we used a generative model called Faraday, which is trained on UK-based load traces. And yes, we create the data set with it, and we also grow it by doing some augmentations. So we scale the overall load, and we also shift the peak in time, because we only have UK-based data, but we want to generalize the model to international data. So we look at different eating patterns, which mainly determine the peak in the evening and around lunch, and we shift our UK-based curves according to that. So here you can, for example, see Spanish curve, which where they eat much later on in the evening. By doing so, we just hope to approximate what might happen outside of the UK. Also, we scale it quite aggressively, because in the UK we have an average consumption of around 2,500 to 3,000 kilowatt hours per year, whereas in other countries like US you would have over 10,000 kilowatt hours. It's almost 4 times as much. Yes, so we also wanted to be a bit robust to that. Then we train on EP usage. So here the model is only trained on some metadata, like how many trips you do per week, average distances, battery capacity, and also charging policy. So the charging policy determines when you charge your car, and it directly affects your load curve. We define 5 different charging policies. The first one being arrival, which is just simply you arrive home, you charge your car to 80%. Then the second one is arrival limit, where you also charge when you arrive home, but you only charge until a limit such that you can leave for common trip distances. By doing that, we kind of leave some space in the battery to charge when there's excess production later on in the day. Then we have the departure policy, where the user has to specify a departure time by which the EV has to be charged at 80%. Initially, it's only charged from excess solar, and then when that time comes closer, it also takes electricity from the stationary battery or from the grid. And then we have bidirectional, which is charged in the same way as departure, but it enables feeding electricity back to the building when there is insufficient production. And then finally, you can also specify if you don't have an EV. The model is only trained on that metadata, but to run simulations which we need for labeling, we have to also create traces of EV usage, which is arrival times and departure times over 1 year. And we do that using Spaghetti, which is a tool developed by Anais and Kesha.
Another thing about the household load, you considered crowdsourcing that data also, because at least in the UK, some electricity suppliers will give you fine-grained load data from your smart meter. So I can download a year's worth of half-hourly meter readings, I think, from my electricity supplier.
Yeah, maybe that would be an option. I think there's just a lot of privacy concerns, because you can tell a lot about the people's habits from just the local. But yeah, I mean, if people are willing to give up that information,
I could imagine some people
yeah.
volunteering, possibly.
Possibly.
Can you not then, or like fine tune the model just on local data after doing like a general data path?
So the people don't have access to the data in the first place, right?
Oh,
Yeah.
Well, I mean, with us, I can just download it from the website to my
Yeah, this is just so Faraday has actually developed the octopus, and what they've done is they've taken all of the load data for the largest university provider in the UK
Right.
now. And so they're giving us anonymized load traces
Oh, I
across.
see.
Yeah.
Oh, so that they've already aggregated.
They've already aggregated and anonymized it, so it is from them.
Oh, that's cool.
I've built a machine in my house which monitors my load every second.
Are you willing to give it to us? So in 2010, my students and I built devices to monitor every 6 seconds the household load, because there's no load for them. So we deployed it in about 12, 15 homes. And so I went and actually did that. So I have very fine-grained load data from about 15 years ago.
Yeah.
It's a pain in the neck, and there is a huge privacy issue that nobody wants to. People have shown if you have 1 second data, you can even know which TV channel you're watching, for example.
I don't watch TVs. Well, I can say I want my fridge turns on.
So
and
there's
off, which is quite
a
interesting.
classic image of a person in, it's a same picture taken in Texas. There's a woman with a gun holding it to a meter installer. She pulled out a gun and said, "Don't you dare install a smart meter in my home." And in Germany, smart meters are not allowed until, even now they haven't fully installed smart meters as far as Germany is held out amongst all other countries. They say no smart. My smart meter is installed in a Faraday cage. So very cleverly, the architect designed a metal box with the smart meter, and so every month I have to open the metal cage and read the meter and put it in. So this is how architects enjoy,
Yeah,
screwing up smart meters.
yeah. They can't install it in my house. They've come out and looked several times, but apparently something about the way the boxes are that they can't do it.
Right, so that's why these load curves are hard to get. So what we're doing is that I go back to Martin's point is that the crowdsourcing would be great. There are many concerns for access to load and load curves, and so we are using what is the best we can do. And maybe you should explain ALPG a little bit. Are you going to talk about that? Or?
I'm gonna touch on it later.
Okay.
Just to finish on that point, when we got a heat pump installed, I was actually asked to upload the hourly load or half-hourly load data
Okay.
to the company doing the installation because they needed to check that it wouldn't
Okay.
overload the grid or
Okay.
our home city connection or something like that.
Okay.
So I'm already sharing this data with some random installer. I'd be very happy to share it with you.
Let's hope they delete it afterwards.
Yes, okay, so the final data we train on is the self-sufficiency ratio, describing how much of your load you want to have met by the PV production. We use a range of 20 to 90% because we don't want to go fully off-grid, because the simulators will tend to oversize, because if you really want to be 100% self-sufficient, you would usually also do some lifestyle changes, maybe think more consciously about when you run high usage appliances, which we don't consider in this work, so we limit it at 90%. So now we create like random combinations of all of those data types, and we run simulations to get an optimum sizing for the battery and PV. We use a simulator by Brett1 for the no EV case, and an adapted version of SolarFit for the EV case. So both of those simulators were developed by previous students of Kesha. Now we have a lot of data. Those load and PV generation curves are at the resolution of 1 hour over 1 year. So combined, that would already be over 17,000 values to train on. We need that to run simulations, but we don't necessarily want to train on that much input. So we want to compress it, and we compress it by using the fast Fourier transform. A couple of months ago, Professor Minhua Shen came to visit Kesha, and he suggested this, so we tried it out, and it worked very well. So essentially what we do is we take about 10,000 samples from our training data, and we compute the Fourier transform for both the PV generation and the load trace. And then we get the Pearson correlation coefficient between every frequency in that Fourier transform and both ground truth types. We do that because we want to find the frequencies which are most relevant to our outputs. And here you can see a plot showing the absolute correlation and the frequency. So you can see that some values have a very strong correlation with the outputs, especially some of those here. So the first one being the mean, and then like daily, 12-hourly, 6-hourly, 4-hourly. You can see that it's the same frequencies which are important for both load traces and solar traces and types of sizings. So for each of those pairs, we select 32 frequencies which are the most important, and we remove the duplicates, and we end up with 84 frequencies. Now we were a bit worried about maybe some frequencies being important in data which is not so well represented in our training data. So we also add the 16 frequency magnitudes, frequencies with the highest magnitude to our training data. So this will differ between all of the samples, but it just gives the model kind of an idea of if there are other important frequencies that might oversize a little bit. Yes, so here you can see the model architecture, which is extremely simple. We tried some other architecture like Transformer or LSTM, XGBoost, but we found that this somehow worked best. Maybe because our training data is not that large. But yes, so essentially you get the Fourier transform, you concatenate it for both the solar and load traces, and you pass it to the time series MLP. And separately, you pass the EV metadata and the self-sufficiency rate ratio to another MLP, and you can get the optimum sizing. So back to our system pipeline, we now explained kind of how the model works, and I'll now show you a demo of the whole application. So this is it. You have kind of 3 types of input. The first one being address. You can put in your city or exact address, doesn't really matter. And here we already checked that we have weather data available, and we fetched that from PV So that works. And then we have to put in some data to approximate the electricity usage. It would, of course, be perfect if you do have like your exact load traces, but many people don't have that. So we approximate it with a tool called ALKG, which is developed by the University of Twente. And essentially what you do is you specify a household type, which consists of your employment and how many people live in that household. And then it initializes a simulation of those people. And with certain probabilities, they will be at home or away for work. And if they are at home, there's other probabilities for them to turn on high consumption appliances like the oven or the microwave, depending on the time of the day. So those statistics are based on Dutch data. So those approximations will also be closest to what you would see in the Netherlands. And you can modify the usage here and add an induction stove. If you know it, you can add your yearly consumption, and we will scale the curve accordingly. And then we can specify if we have an EV, and it will ask you for the commute days, one-way commute distance, number of short trips per week like groceries, and average one-way short trip distance, let's say 10 kilometers, and EV battery capacity. And then you can get the sizing. And you can see that it recommends a system here for the panels. Oh, my mouse is a bit delayed. For the panels and the battery. This is based on the cost curve that we create. So we get predictions for all self-sufficiency levels between 20% and 90%, and we plot the estimated costs. and it will get the maximum curvature point as kind of the optimum sizing in terms of cost. Yes, and then you can change charging policies. Maybe you don't have bidirectional charging, then you can go to the departure policy. And you can also look at the yearly savings curve and the payback time curve. You can vary your grid tariff, so the tariff you have to buy electricity and to sell back if you have excess. And you can see that, for example, if we increase that, it will be more attractive to have higher self-sufficiency level because we'll have more excess electricity you can sell back to the grids. If you maybe have a budget, you don't have £5,000 to spend on it, you can vary and look at different sizings and their costs and benefits. And yes, so if you find a sizing that you like, you can validate your selection and it will run the simulation to ensure that those sizings are accurate. But this will take a couple of minutes, so I think I'll go back to the presentation and we can check later. So now we will look at how well the model performs. As we explained before, we trained on UK-based load, but we augmented it to kind of approximate what might happen in other countries. So we want to see how well we did that. We're testing on the Faraday data. This is just a test split of our, essentially the same data we use for training. And then we have ALPG, which is what we use in the application, which is based on the Netherlands. And we have the data set of 25 buildings in California. So the US especially has a very different load curve than we see in UK or in EU in general. So they have much higher consumption. They have appliances we don't usually use a lot, like air conditioners. So this is really an out of sample test to see how it looks. So here you can see the performance. We compare against a baseline model, which is a model we presented at e-energy a couple of weeks ago. It was pretty much the first attempt of building a model for this. And it just takes the load curves and the PV generation curves. It doesn't do Fourier transform, and it has a fixed self-sufficiency ratio, which is 85%. So because it's a bit limited, also the predictions will be more focused on one point. Then all of those are our current model tested on the Faraday data, the ALPG and the Beacon Street. You can see that it does extremely well on the Faraday data and even on the ALPG, which is Dutch data, it does extremely well for PV sizing, a bit worse for battery. So maybe if you can't see, all of those are for PV sizing and all of those are for battery. And we can see that there's a couple of outliers here for battery, but overall it does very well. The MSE and MAE is not much worse than for Faraday. And then we can look at the Pecan Street, California. So here, still very surprisingly, the PV sizing is extremely good. So there's very few outliers. I plotted 3,000 points here. So if this has like few outliers here, that's not really a lot. However, if we look at the battery, it's a bit worse. So it has quite a strong bias, which means that it tends to undersize the battery, which might be due to some frequencies not represented well in our training data, which are important on the US data.
You explain the boxes.
Yes, the boxes. So when you get the sizing, you always have to round up because if you round down, it will be below your self-sufficiency targets. And batteries and panels will be sold in fixed increments. So for battery, we usually have 400 watts per panel. And for battery, there are some stackable batteries where you can purchase single units, and those units are about 2.5 kilowatts on the lower end. So we plot one of those gray boxes to show that all of the predictions within that box will be rounded to the same as the ground truth. So if you put this into context, because the increments are so large for battery, actually a lot of the predictions will be rounded to the same product. as a ground truth. So yes. We also look at the geographic error distribution. Here we use the Faraday data set and we plot the error based on the location of the PV traces. And we can see that for the PV mean absolute error, it's pretty like there's not much difference. But if you look at the battery, still not a lot of difference, but in the very north, you can see that the error increases a bit. This might be due to just a lot of fluctuations between the seasons and even during the day. And also maybe because we had a lower number of samples in that climatic region. Now the latencies. So we saw before during the demo that there's pretty much instantly a response from the tool. So on average, it takes about 3.6 seconds to get an overview. Of which almost all of it is due to the ALPG. So only 38 milliseconds are data processing, model inference, and processing the output, which is extremely fast. So if we compare this to what we would get using the simulator for the same task, we are now 600 times faster than simulations.
What is it running on?
Which is my laptop.
Oh.
600,000 times faster.
600,000 times.
Yeah, there is 600 times. Yeah.
600,000 times.
Yeah,
Sorry.
it's quite huge.
Yeah. So yeah, with this simulator, it would take over 6 hours. After waiting 6 hours, you might have already forgotten, or you might not want to change like your EV configuration to try out different things. So that's kind of the main cool thing about this. Now to future work. So our current model doesn't consider the topology of the roof at all. So it doesn't consider the orientation, the tilt. Might also be that there are some trees around the house which has shading onto the roof. So to address this, we want to create a new data set, which includes that kind of data of the surroundings of the house. One of the master students supervised by Kesha, her name was Hetong, she built a simulator where she gets optimum sizing, considering all of the shading you might have and the orientation and details. So we want to use that to label our new data set. We use data from Switzerland. So Switzerland has data sets of kind of a point cloud of all of the elevation points in Switzerland at the granularity of 4 points per square meter. And we connect neighboring points to create a mesh, as you can see here. Then we take a separate Swiss data set, which contains 3D buildings of all of the houses in Switzerland. And we can map those roofs onto our surroundings. And we want to train the model by indicating where the roof is, where we want to place panels, and also show the height of the surroundings. Yeah, so if you have any suggestions for that, please let me know. Yes, so this was pretty much all of it. Since this is our last meeting, and I won't be back for next term, I wanted to thank everyone in the group, especially Kesha, for being very welcoming. And yes, I had a really nice time in Cambridge, so thank you.
Okay, thanks. We have time for more questions if anybody has more. Yeah.
Sorry, I think I missed the part. How did you build the thing, if I can call that like an emulator, to replace the simulator to make that much more faster?
So essentially, we use the model instead of simulate. Oh, what do you mean exactly? Do you mean?
Did you replace the simulator with some like neural network?
Here we use a model instead of simulation. So previously there was no model available to do that. So that's kind of our contribution, but we still use the same simulator as before for the verification, because creating all of those curves would take around 300 simulations. Each of those take like 1.5 minutes. So it's not.
Sorry.
And so it's not realistic to do it with the simulator, but we still want to give kind of ensure the user that it's 100% accurate by giving them the opportunity to do that verification step in the end. So this runs maybe 2 minutes and then you can verify. Usually it will be quite exact. So here you can see, for example, the battery the panels we predicted was 3.8 and the ground truth is close to 4 and the battery was actually perfect. So it's usually not a lot of difference, but in case that there are outliers, we don't want to suggest that.
The model is like a set of neural networks to surrogate the original equations.
And she showed the NLP, I don't know if you.
Oh, that part. Okay.
Yeah.
Another question.
Oh, I believe that in one of the previous slides, you had the time slide that had UK time, German time, and Spanish time. Are those all normalized to UTC? Because if I remember correctly, Spain is like in the historically speaking, it's in the wrong time zone. So I'm not sure whether that would affect what predictions you make.
It's all based on UK time zone.
Oh, so you shift the times.
So essentially, in the UK, we have an average dinner time of at 6 o'clock, whereas in Spain, I think it was at 9. So we shift back 3 hours.
I think the question is something like this. Spain is actually west of UK, but actually has a time zone corresponding to the east. So what we think of as 9 p.m., they call it 10 p.m., right? So dinner time for them is late because the sun sets late. So the solar has also got to be aligned to make the sun set later in that time zone.
I mean, for the solar, we combine our load traces with random solar traces.
Oh, okay.
So there is no really alignment between patterns necessary.
Oh, okay. So household load is based on civil time, and then the PV generation was based on solar time. Okay, cool.
So what would happen is that in Spain they would eat later, but the sunset time there would be sort of UTC. I guess it's time zone adjusted, presumably.
Yeah, I think it just took the statistics out of the paper where they adjusted it.
Right, but so PV watts is giving you it's giving solar production for time step. That time value is the universal time.
No, it's always the
Local time.
location you ask.
Okay, got it. So it's local time. Thanks. That's a good question. Yeah, but,
The US increased energy usage. If you remove air conditioning from that, is that a thing we can do? There's a follow-on question to that. Do American households generally use more power, full stop, even discounting air conditioning? Or is that not something we know for the environmental?
I can speak to that because I was in Canada and I moved to the US for many years as well. Generally speaking, US uses per day, they use on average 20 kilowatt hours per day. That's the normal. In the UK, in Europe, average is 7 kilowatt hours a day, and UK is actually about 5.5. And Cambridge is even lower than that, actually. It happens because the differences have to do with level of insulation and the kinds of specs for. So all of this dual pane plant, for example, it's common to have dual, or in some places triple pane. The US is almost everywhere single pane.
Still.
Single pane.
Okay, so even if you the follow-on was if you take air conditioning out of it, they're just worse anyway. So that was
Also, the houses are much larger. So typical US home would be on average 2 to 3 times larger.
Oh, okay. Because the thing I was wondering or curious about in the future is these are sizing systems that will last 10 years, 20 years. The panels could last 50 years. Air conditioning is coming to Europe. So, I hope so.
Well, heat pumps, I believe.
Well, no, but I mean, heat pumps. The installation of air conditioning is domestic aircon installations in the UK is a massive industry at the moment, just because of the effects of global. The thing I was wondering is that of course, when you fire it during the day, steals your ability to charge your battery. So as to whether that's something that's relevant to the sizing calculation, whether that's a future thing that.
I mean, did shift the UK
Yes,
load
do they have
curves
to?
quite a bit, and we did that by scaling it, also by adding kind of a higher base load to every time step. So if you do have air conditioning, you will pretty much always have a higher consumption.
So it's as gloriously simple. It's just a matter of
Yeah,
increasing it to allow for that possibility.
I mean, you have the heat pump step, right? You can add a heat pump if you want to,
Yeah.
which will be
Yeah.
heating and cooling.
Mm.
but yeah, I mean, it's a general problem. You do your sizing based on what you use now.
Mm.
In 10 years, you might get air conditioning, so you can't really anticipate for that. But we do compute robust sizing, which adds a buffer essentially. So it should be still applicable for like.
So we do it to the show about. There's actually.
So the thing that interested me was when you were comparing the US air conditioning was the bit that was mentioned, but it says there's a lot more than that. They're just rubbish.
It's the size actually.
Yeah, it's the size as well.
Bigger houses of which aren't as well. So.
Yeah. Oh, okay.
Any other questions? Anybody online have a question? I don't know, Andre or Frank? No, no.
I had a question. This is Andrea talking.
Yeah, go for it, yeah.
Okay. Well, thank you, Julia, for the wonderful presentation. My question is a little bit about maybe your testing data. So correct me if I'm wrong, but you're training this model on UK only related data, and then in your testing, you're seeing if it would kind of extrapolate to other regions. Is that correct?
Yes, we train on the UK-based data, but we do some augmentations to kind of hoping that it will generalize to other countries.
Yes. Do you think, or have you kind of tested out if you start including some of that data as well, if that helps with the generalization? I mean, it does pretty well as is, but just curious.
Yeah, I mean, that's something I think it would definitely help. I think the main problem is just the size of the data sets we can get from other countries. So for example, under the educational license, I have about 50 buildings from the US and I have about 20 buildings from Pakistan. But it's just nowhere near the amount of traces I would need to train a model on. And I also wanted to keep some of the data to test on. That's mainly why. But if there were more data, I think it would be great to include that.
Yes, that makes sense. And I guess a follow-up question, if you could kind of go back and since I know your time with Cambridge is ending, what would you kind of change, or is there anything that you would consider including in the model as input, or yeah, anything like that?
I mean, I did extend it 1,000 times, so I feel like I already did adapt it a bit to what I missed initially. But I think especially kind of the future work we have planned will be important to include, because that is a very important factor if you have shading on a lot of your roof segment, or you don't have a segment pointing to south. That will affect your sizing. So I think it will be very cool if we could include that.
Yes, that sounds good. Looking forward to it. Thank you.
Yeah.
Great. Anybody else? Okay, in that case, thank you.